Okay, welcome back to our last set of notes for Chapter 10. We left off drawing boron trifluoride, and we left off with the what's come to become pretty common sound of my dog whining at me when she gets tired of me making videos. So let's look at another one. We looked at boron trifluoride last time. We drew it, we said it was symmetrical, it should be non-polar. That's where we left off, and we were right. All the arrows face away from each other. It is pretty symmetrical, and you can see that the electron distribution around it is pretty even. So that would be nonpolar. So how about CH2Cl2? We start by drawing our Lewis structure. Looks kind of like this: 2 hydrogens and 2 chlorines, and so the carbon's more electronegative than the hydrogens, chlorines are more electronegative than the carbons, and so we do have a dipole moment. Now, if you put a hydrogen over here, and a hydrogen over here, and a chlorine over here, and a chlorine over here, it might not be the case. But the way they have it drawn, this is definitely going to be polar. So here it gives you dipole moments of some polar molecules, and then their shapes as well. Okay, so let's look at Lewis theory a little more. Bonding in H2 and F2, we're going to share 2 electrons. And so with H2, here our bond length you can see is quite a bit shorter with hydrogen than it is with fluorine. That makes sense because fluorine's got a lot more electrons in its electron cloud. And here you have 1s orbitals overlapping and 2p orbitals overlapping. 1s are much smaller orbitals, and so we get a lot shorter bond length, which kind of makes sense. And so valence bond theory, which is what most of us have a pretty good understanding of, and is really what we've been taught since physical science, tells us bonds are formed by sharing an electron from overlapping orbitals. Here's a graph that shows you potential energy change of 2 hydrogen atoms as we look at how far separated they are and how much potential energy they want to have. And so here, if they're closer, forming that bond, their potential energy is really very low. And that's pretty stable. That's a good place to be. Whereas if you try to separate the 2 hydrogen atoms, they get quite a bit of potential energy. So we're going to probably find them down here. So how does electron density change as they approach each other? Here you can see one hydrogen nucleus, they start to approach each other, and they're sharing this electron more and more, till the electron's here. And you can see why it's non-polar. I mean, it's very evenly shared, and it's not much of a separation of charge. It's blue over here and blue over here, red in the middle. It's a non-polar molecule. So let's look at NH3. This will be a little trickier. Here we want to get to P6, and so we're going to have to make 3 bonds, and that's what we're going to do. And so here is what your lines would look like. You've got your 1s2, your 2s2, your 2p1, 2, 3. So we really want to form 3 more to fill that. And so hydrogen's 1s1, and so you fill 1 hydrogen, 2 hydrogens, 3 hydrogens, and now we're stable. So if the bonds form from the overlap of the 2p orbitals on nitrogen with the 1s orbital on each hydrogen atom, what would the geometry be? And you can see what it would look like here. There's a p orbital, there's a p orbital, there's a p orbital. And if we use the 2p orbitals, we would predict that it would probably be about 90 degrees. But actually our bond angle is 107.3, and that is of course because nitrogen has hybridization. And so hybridization is going to be explaining what these actually look like compared to what the Lewis structures say they should look like. And basically, to make a hybrid is to mix 2 types. So to mix 2 types of atomic orbitals to form a new set of hybrid orbitals. So it's no longer an s orbital or a p orbital, it's an sp hybrid orbital. It's kind of like it's not a Labrador or a poodle, it's a labradoodle. It's both and neither. So that's what a hybrid is. And we can do the same thing with electron orbitals. So sorry for the weird example, but if you mix 2 non-equivalent atomic orbitals like s and p, you can make a hybrid orbital. They have a different shape. The hybrid orbitals, the number of them is equal to the number of pure atomic orbitals. And covalent bonds are formed by overlapping hybrid orbitals with atomic orbitals, or overlapping hybrid orbitals with other hybrid orbitals. So here's how you can look at how we could form an sp3 hybrid orbital. This is s. It's a sphere. You're familiar with that. Here's p orbital, which is a dumbbell. You're familiar with that. Here's a dumbbell along the y-axis, which we're familiar with, a dumbbell along the z-axis, which we're familiar with. Now here's something we're not that familiar with. sp. So here's an sp hybrid orbital. Is it a sphere? Not really. Is it a perfect dumbbell? Not really. It's kind of a mix of both, and neither. It's a hybrid. So here's sp3, 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 just showing you different orientations in space. And so when we form these covalent bonds in like methane, we can say that the orbitals around the carbon atom are hybridized. And while it's a little complicated to understand, it's very easy to name, which is nice. And you've probably already done this. In Gen Chem, we did this. We'd say, what's the orbital hybridization about the carbon atom? And you'd say S, sp, sp2, sp3. It's sp3 hybridized because there's 4 regions of electron density. You can look at the same thing here. What's the hybridization about the nitrogen atom? And you look at it and you go, okay, what's my regions of electron density? 1 for the bond, 1 for the bond, 1 for the bond, 1 for a lone pair. Doesn't matter if it's a single bond, double bond, triple bond, that's still 1 region of electron density. So it would be S, sp, sp2, sp3, sp3 hybridized nitrogen atom. And that's what we do there. So you can predict a bond angle thanks to that. So here's how they're formed. The hybrid looks kind of like this, not really a sphere, not really a dumbbell, they're a little different. And here, I could ask you the same thing about beryllium, be S, sp, sp hybridization. And here's the shape of the orbitals, and then here's how it's being used to make a compound. So what about sp2s? Well, we take S, and then we take 2 p's, and we hybridize them to make this same really odd, I guess, bowling pin shape, you could say. And so here it'd be boron trifluoride, which we've drawn already, would be S, sp, sp2 hybridization. So how do you predict it? You draw the Lewis structure. You count the number of lone pairs, and you count the number of atoms bonded in the central atom, and then you just add them up. So if there's 2, then it's sp, like beryllium dichloride, or beryllium chloride rather. If there's 3, then it's sp2, like boron trifluoride. If it's 4, then it's sp3, like NH3, which we've talked about already. And if there's 5, then it's sp3d. You can't have sp4, because remember, a p orbital only holds 6 electrons. Then you got to go to d, d2, etc., etc. So there's 6 sp3d2. Those are hybridized orbitals. And so here's kind of a diagram, shows you what they look like, what their bond angles are. I don't think bond angles are something you're going to need to commit to memory for the rest of your life. I hope I'm not doing you a disservice by telling you that. I don't have them committed to memory at any rate. So here's the hybridization of carbon. We start off with 4 in the 2s and the 2p. In order to make those 4 bonds that we frequently see carbon having, we're actually going to go ahead and move one of these electrons over to here. They call that a promotion of an electron. So we're violating some rules we learned earlier, but we know that carbon forms 4 bonds, so this must happen. Now we've got an sp2 hybridized state, so we can form 1 bond, 2 bonds, 3 bonds, 4 bonds, which makes carbon very useful. So the unhybridized orbital is the gray here, and it's perpendicular to the plane of the green hybridized orbitals. So let's look at ethylene. Here we have carbon, 2 carbons, and 4 hydrogens. And so this is going to be a double bond in between here to complete those octets. And that double bond looks something like this. Sigma bonds are always the first bonds to be formed, and then pi bonds are the next bond to be formed. And so one thing to note, the sigma bonds connect carbons to hydrogens and carbons to carbons, but then to satisfy that octet, we're going to form pi bond, and those pi bonds, it takes 2 of them to make a single line on a Lewis structure. And so it gets a little odd, but there's a sigma bond between 2 atoms, pi bond, electron density above and below the plane of the nuclei of the bonding atoms. But they still do make the bond between the carbons stronger, and they still do shorten the bond length. They're just outside of the plane of just this carbon and hydrogen. They're overlapping like the ends of orbitals, kind of. So here's another view of it. Our sigma bonds are now lines, and the pi bonds are above and below this sort of flat blue plane, and that would just account still for a single line on the Lewis structure, both of these electron densities for the pi bond. And so here's kind of a space filling model to show you where the electrons are. Here's the red above and the red below to show you the electrons here below and above. So here again, we're sp hybridization of carbon because carbon's super flexible. You can do all sorts of things like this. So here we're making acetylene, C2H2. So now we're actually going to have to make a triple bond to make this satisfied octet. And so to do that, here I told you 2 of the pi's makes a single bond, and so we've got a single bond here, a single bond here, a single bond here is the purple, and then 2 pi bonds make another bond, and then 2 pi regions of electron density make another bond. So we end up getting 3 bonds between the carbons and a satisfied octet. And so here's what it looks like in the Lewis. 1, 2, 3 bonds between the carbons. Hydrogens are on the outside. So describe the bonding in CH2O. Okay, so carbon has 3 bonded atoms. It's got no lone pairs around it, so its hybridization is sp, sp2. Even though it's a double bond, doesn't matter. It's still one region of electron density, so that's how we give it the sp2 hybridization. And then here they've drawn out where the pi and sigma bonds are between carbon and oxygen. You'll note that the sigma makes a single bond, the pi regions makes the double bond, and then oxygen's lone pairs are spread out over here. So, sigma and pi bonds. If it's a single bond, it's 1 sigma bond, it's real easy. If it's a double bond, it's 1 sigma and a pi. Triple bond, you guessed it, 1 sigma, 2 pi's, makes 3. So then you can just draw a Lewis structure and count them out. You'll see questions like this in the book and on tests and stuff. How many sigma and pi bonds are in acetic acid, CH3COOH? So you draw it. Looks like this. You see, okay, sigma, 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 and 1 pi. So you just count them up. That's all it is. So there's 6 sigmas, plus 1 sigma up there is 7, and then there's 1 pi. Oops, sorry about that. There's 1 pi right there. So that's all you got to do. Don't have to count those unbound valence pairs, nothing like that. So let's see. No unpaired electrons. Should be diamagnetic, right? So it should not respond to a magnet. This is, of course, oxygen gas. If you look at it, it's really nice and symmetrical, so it shouldn't be polar, and it shouldn't respond to a magnet because it's nonpolar, right? We can't have a dipole and something nonpolar, at least not for very long. So according to Lewis structures, which is the way we understood oxygen for a long time, oxygen should be not magnetic, and this is satisfied octets for both oxygens. It's very strong bond, double bond, and we were fine with that until we took really cold oxygen gas and we poured it down through a magnet, and what we found was, sure enough, that oxygen gas kind of sticks to the magnet. And so it shows that oxygen's actually paramagnetic. It does react to a magnetic field. So that's kind of weird. We can work with it, it's just weird. So what that tells us, though, is that this model is not reflective of what's coming out of this container. If it's resulting in magnetism, then this must have 1 lone electron that does not exist in a pair. And this probably has 1 lone electron that does not exist in a pair. And so this double bond idea, while nice, is apparently not always reality. So we had to come up with a new theory to account for what we're observing here. And it's a tricky one. It's called molecular orbital theory. Bonds are formed from interactions of atomic orbitals to form molecular orbitals. So the idea is basically this. We've known that atoms have an s orbital, and a p orbital, and a d orbital. And we thought we can just overlap S and P's like Lewis structures. That explains everything, but it doesn't. For here, to look at oxygen gas, we have to say, okay, yeah, atoms start with S and P orbitals, but when they form molecules, they form new orbitals, kind of different than S and P, that are separate from the atomic orbitals, and we call those molecular orbitals. So the Lewis valence structures doesn't explain every molecule, and molecular orbital theory doesn't explain every molecule. We kind of have to use them both. So there's kind of the unfortunate part. So energy levels of bonding and anti-bonding molecular orbitals in hydrogen. So the idea is this, we look at, here's hydrogen, how we understand it, and it can be the 1s, 1 electron, and 1s, 1 electron, and when they come together, they've got options to form a sigma molecular orbital, where they form a bond, or they could also form a sigma molecular orbital where they don't form a bond. So orbitals in a molecule that aren't allowing electrons to bond. And so that's a little odd, but if you look at this is your energy levels here. And it's always a lot more energy efficient to form this bond than it is to form an orbital that is anti-bonding. That's the little star here. So to form an orbital where there's no bonding of electrons happens, but it's generally a lot less energy efficient than it is to just go ahead and form the bond. So the reason that we decide that electrons can behave this way is because electrons are particles and they're waves. They're both and they're neither, you know. That whole wave-particle duality thing we've talked about. So waves can go through constructive interference or destructive interference. So for this model, constructive interference is where the peak of one wave is in sync with the peak of another. So if it were sound, it would become a louder sound. Here, constructive interference with the wavelengths of electrons gives us a bonding sigma orbital. Now, the bonding molecular orbital has lower energy, greater stability than the atomic orbitals from which it was formed. So it's actually better to be in this sigma molecular orbital than it is to be a lone hydrogen by yourself with just your 1s orbital. So now the other type of interference is destructive interference. So here if the wave, the peak of one wave hits the trough of another wave, they're out of sync. And those waves would kind of cancel each other out. If it were a sound, it'd become much quieter, but this isn't a sound, it's an electron. And when these electrons' wavelengths don't match up, they form anti-bonding orbitals. Now you'll notice that the shapes are still pretty similar. They're still kind of circular, but they don't overlap the way that these do. And so we end up getting electrons that form orbitals that aren't actually bonding with each other. And so that is the sketch right here. So the anti-bonding molecular orbital has the higher energy and a lot lower stability than the atomic orbitals from which it was formed. So from an energy point of view, this is best, this is okay, this is not that good, but they happen sometimes. So here's constructive and destructive interference, kind of the thing I already explained to you here. Basically, wavelengths that are in sync, peak matches peak, trough matches trough. The resultant wave is huge for its amplitude. The other waves, a peak matches a trough, and a peak matches a trough. Those waves cancel each other out. Flat line is a sum of 1 and 2. That's destructive interference. And so here's two ways this could work. We could go through destructive or constructive interference, and as a result of that, we're looking at two P's now, so instead of one circle we're dealing with two. They could either form a bonding sigma orbital, or if they went this route up here, they could form anti-bonding sigma orbitals. Now it's a lot more energetically favorable to form the bonding, and so that's probably what they're going to do. Here we have the same thing, destructive up here, constructive down here. And if they form anti-bonding, it looks something like this, all four away from each other. If they form bonding, we get that shape that we're familiar with before, where we saw pi orbitals. Now look at this mess. Doesn't that look like fun? General molecular orbital energy level diagrams for second period homonuclear diatomic molecules. Homonuclear means same nucleus, so lithium bonded to a lithium, a beryllium bonded to a beryllium, a boron bonded to a boron, that kind of stuff. They have a particular order you have to fill these in. It's not just lowest energy to highest energy, which is really a downer, but I'm not going to make you memorize that because I think that's crazy, and I don't want to memorize it. So, configurations. The number of molecular orbitals formed is always equal to the number of atomic orbitals that are combined, and the more stable the bonding, the less stable the corresponding anti-bonding molecular orbital is going to be. We're generally going to proceed from low to high energies, and each molecular orbital can accommodate up to 2 electrons. So we use Hund's rule, which is 1 up arrow, 1 up arrow, 1 down arrow, 1 down arrow, when adding electrons to those molecular orbitals at the same energy. And the number of electrons in the molecular orbitals is equal to the sum of all electrons in all the bonding atoms. And so we can use something called bond order, where we look at whether or not putting electrons where we are is feasible. Basically, bond order is 1/2 the number of electrons in bonding minus number of electrons in antibonding molecular orbitals. If you get numbers that are negatives or 0, it's probably not going to happen as a molecule, but 1/2, 1, 1.5, 2, those are pretty likely. So then here, we'd have to figure out our bond order, so we use this equation and we say, okay, what's 1/2 of 1 minus 0? Okay, it's 1/2. So is hydrogen plus a possible structure? Yeah, it probably is. How about this one here? We got 2 minus 0. half of that would be 1. So is hydrogen gas something that could work with molecular orbital theory? Of course it is. Helium 2 plus, we've got 2 minus 1 would be 1. Half of that would be a half. And so we're just using this equation here. So that's a plausible structure for molecular orbital theories. Here, helium 2, we're looking at 2 minus 2 is 0. 1 half times 0 is 0. Probably not going to form molecular orbitals. And helium doesn't, of course. And so then here's our kind of showing you the order in which they're filled and some representative elements here. So delocalized molecular orbitals. They're ones that are not confined between two adjacent bonding atoms, but actually extend over 3 or more atoms. So it's kind of weird. It's basically a bond that's not just stuck between 2 carbons or 2 nitrogens or 2 anything. So this example here is benzene ring. If you remember organic chemistry, it was this fellow. We drew him a lot in organic chemistry and Gen Chem. He looks like this. 1 line, and then 2, and then 3, and then 4, and then 5, and then 6, and then that. And we drew him all the time. He was in so many structures. And the reason we draw that circle is because this is kind of like a double bond here, and kind of like a double bond here, and kind of like a double bond here, but it's not stuck there. It can be here or here or here, and it actually resonates in between those. And here, this definition is they're extending over 3 or more atoms. And so where do you say, man, where is this pi bond hanging out? And the answer is everywhere in here. So we draw the circle like that. That's a delocalized pi orbital, and benzene is probably our best example of that. Here's the hydrogen sticking off of it, and the pi bonds extending around the inside, and here the side view above and below as well. That's that pi bond right there that we're seeing, and right here that we're seeing. And so it's delocalized. It extends over many. Here's electron density. Our hydrogens are the blue positives, and then the double bonds give us electron density kind of above and below a little bit here. That's the red up there. And so then our carbonate ion is the same thing. We have a pi bond that extends over the carbon and the oxygen and the other oxygen. And so we get this delocalized bond that's just kind of taking up the whole molecule. And so then the last thing your chapter talks about is buckyball, Buckminster fullerene. Basically, it's just another form that carbon can take. Carbon can be in sheets like a graphite pencil, a mechanical pencil. Of course, it's not lead, it's graphite. You just scrape the carbon off and you scrape that little sheet of carbon atoms, and it leaves, a mark on your paper. If you bond all of these to each sheet below it and you bond them all to each other, then you get something like diamond that's super, super hard. And then we get another structure of carbon, which is this buckyball. It looks a lot like a soccer ball, and it has all these little 5- and 6-sided alternating shapes. And it's become rather useful in organic chemistry and in synthesizing new technologies and flexible fibers and things like that, because you can build really long tubes with it, or you can build circles with it, and you can put other things in those circles and use it as delivery methods for all sorts of technology. And it's a really cool thing. It's just a new form of carbon, basically.